Ladies and gentlemen, please welcome Professor Stephen. I request one of my colleagues to present sir with a bouquet.
And I'd like to thank the organizers for inviting me here. And as you may not know, this is my first trip to India. So I want to talk about the P versus NP problem. That's what I won the prize for, the award. And first of all, just want to point out this is in the mathematical, it's a mathematical question. Does P equal NP? I'll explain what that means. And in the mathematical community, it's a well-respected question in mathematics. And it's one, in fact, it's one of the 7 open questions that each is worth $1 million that was offered by the Clay Mathematics Institute. So what are P and NP? So roughly, for a first rough explanation, P stands for polynomial time, and we think of it as the class of easy computational problems that can be solved relatively easily on computers, and NP stands for non-deterministic polynomial time. NP does not stand for not P, as there's a possible confusion there. In fact, every problem in P is also an NP. And so P is a subset of NP, and the NP problems are the ones that can be solved by a non-deterministic machine that can guess things, but then it has to verify the guess. Okay, so here I'll explain more about P and NP and why it matters whether or not P is NP. So the P problems, examples of problems in P, arithmetic problems, addition, multiplication, they're easy to do. Computers have no trouble even with millions of digits. And with square roots, it's something a little less obvious, but there are algorithms for solving square roots very fast. You know that from your, every calculator has a button, you just instantly get the square root. But the square root is an interesting example because it's not immediately obvious how to find the square root of a very large number. Let's think of hundreds of digits. One thing you can't do, and even computers can't do, is to use brute force. You successively square every number until you find past the square exceeds the number you're trying to find the square root of. So if you have 100 decimal digits, no computer is ever going to do that before the universe expires using this method. But of course, there are other very fast methods for finding square roots. The best is probably due to Isaac Newton, where it's extremely efficient. So the point is, the method used by computers is crucially important if we want to solve it efficiently. And the most obvious method is certainly not the one that is going to be efficient. So another good example is this is not, sorry, the mic is on, isn't it? Okay, so they're saying they can't hear me. Okay. put it up here. How's that? Is that a little better?
Yeah.
I just have to talk louder. Okay, so let's consider another problem, that is factoring every number, every positive integer can be written as a product uniquely. In fact, as a product of prime numbers. And so the interesting computational problem is to find the prime factors of a given number. And this is a problem that isn't so easy. It's not known to be in P, as a matter of fact. And in fact, the security of the RSA encryption scheme depends on the assumption that you can't factor large numbers easily. And there's an illustration of that. The RSA organization used to advertise publish large numbers, which were products of 2 primes, and then challenge the world to factor them. So this is, I think, the record, the public record happened in 2009 when they, this particular number was a product, it was 232 digits long, and it was a product of 2 primes. And so it took, the people who factored it took hundreds of machines in 2 years. So that's an indication of where we stand, at least a few years ago, in factoring numbers. So that's a hard, currently it's a hard problem seems to be a hard problem for computers to do. And so speaking, one of the major successes in my field, computational complexity theory, where we try to do problems that are difficult or are not easy, is the concept of public key encryption. And so this was introduced by Diffie and Helm in 1976, and the particular method used RSA in 1978. So the idea is it's possible to securely send an encrypted message in a public channel without the parties agreeing ahead of time on a secret key. And of course, the security depends on some assumption that is computationally intractable for computers. So, and then just pointing out that earlier on, of course, there was plenty of encryption going on, but the 2 parties had, the people doing the encryption and the receivers had to agree on the secret key ahead of time in order to make it work. So how does public key encryption work? An example is PayPal. You can send your credit card number securely over the internet, presumably by PayPal, even though the internet itself is not secure. People can eavesdrop on what you send. So the way it works, PayPal sends, PayPal's computer sends a public key. They use random bits to find both a public key and come up with a public key and a private key. And then the public key is sent to you. The PayPal's computer sends some long string of digits to your computer, and that's insecure. It's assuming that the other people on the listening in can find the public key. Your computer uses the public key to encrypt your credit card. There's your credit card number. So it applies a function to these 2 things and some random bits. And then it sends this encrypted code back to PayPal. And PayPal is able to use its private key to recover your credit card number. But the assumption is even those eavesdroppers that know the public key, even though the public key can be used to encrypt, it can't be used to decrypt. And so it's assumed to be computationally infeasible for just knowing the public key to recover the credit card. And so in the RSA scheme, part of the private key consists of generating large random prime numbers of several hundred digits each. Those numbers are P and Q. And then the public key consists partly of just computing the product of P and Q. So, and then the assumption is knowing the product, it's computationally feasible to factor. And that seems to be the case, at least at present. But we can't prove it, and that's what the mathematics of computational complexity, what we're really trying to do is prove that some problems can't be feasibly computed, and that's extremely difficult. And an example is certainly factoring. All right, so computational complexity theory classifies problems according to the computational difficulty. And so the standard class P that we talk about in the P versus NP was first defined independently by Alan Cobham and Jack Evans in 1965. So the mathematical definition is it consists of problems that have an efficient algorithm. And efficient means that the running time of the algorithm is bounded by a fixed power of the input length n. That's why we call it a fixed polynomial. That's why we call it polynomial time. And so, and here's the number, would be the number of digits, for example, in the prime factorization problem. It's the length of the input to your computation problem. And if there's an algorithm that can solve the problem using some fixed power of n, then its problem is in P. And so lots of examples that we mentioned are polytime problems, arithmetic problems, square roots, shortest path, multiple folds, pattern matching, vast Fourier transform, and interesting, recognizing prime numbers turns out to be in P. And that's a result. That was an open question finally solved by the Indians in 2002. And there is, based on number theory principles, a polynomial time algorithm to recognize primes. But that's different, of course, than factoring a number of primes. Recognizing primes is easier than factoring. Okay, now so what about NP, nondeterministic polynomial time? So that consists of problems that can be efficiently verified. And I think it's good to think of NP problems as search problems, where you have an exponentially large search space and you're trying to find a solution in the search space to your problem. And an example is factoring. In factoring, the search space would be the set of all couples of prime numbers, and you're trying to find the right one that represents the prime factors of your number. And but for a search problem to be in NP, you have to have a fast way of verifying the solution. If you find it somehow or somebody tells you it, you can verify the solution in polynomial time. So that is the condition for an NP problem. It may be very hard to find the solution, but if you find it, you can verify it easily. And so prime factorization is an NP problem. In general, cracking cryptographic protocols tends to be an NP because if you can guess the key, usually you can verify it. And there's all kinds of scheduling problems that are NP problems, important NP problems, where now to formulate the problem, like for scheduling trucks, you would have a bunch of destinations that you're trying to deliver goods to, and the scheduling. And then you say, can you organize all the trucks to hit all these cities within a given total mileage limit or something like that. And again, if you can find the solution, you can verify that, that it can be done. But the search space is huge, it's exponential. So roughly P are the problems for which the solutions can be found efficiently, and P are the problems for which solutions can be efficiently verified. Now the open question is whether every problem in NP is in fact in P. So if you can verify the solution when you find it easily, then in fact you can find it. Now we think not. The examples, there's lots of examples where this seems to be the case. And, so the conjecture, we complexity theorists conjecture that P is not equal to NP, that there are problems in P that do not have polynomial time solutions. But what we'd love to do is prove it mathematically, that there are problems in NP that are not in P. And that's the open million-dollar question that the Clay Mathematics Institute has offered. Can you prove P not equal to NP? Or, they'll, by the way, if you can prove P equals NP, they'll give you $1 million too. But we tend to think that's probably not the case. But I just mentioned here that proving something isn't P, we have an idea how to do it. We just give the algorithm and prove that it's fast and works. But it's much, much harder to show there is no algorithm, efficient algorithm for a problem. That turns out to be extremely difficult. And one reason is that there are search problems. An example was finding the square root, where you might first think you have to try a lot of all possible numbers, but of course they're the totally easy way. And another example is the matching problem, where one way of it's really a graph problem, but one way of saying it, if you're given a large group of people and we want to pair them up to work on projects, we know which pairs of people are compatible, and if possible, we want to put them all in compatible pairs. So if you know graph theory, this is just a graph problem. The nodes in the graph are the people, and the edges connect any two people that are compatible. So you're just trying to find a collection of edges, disjoint edges that fits every person. And again, brute force is not going to find this in any kind of polynomial time, because there are exponentially many possible sets of edges, pairs of people that might be the answer. But it turns out again, and the same Jack Edmonds who posed the problem P proved that there is a very efficient algorithm for solving the matching problem. Okay, and that's not at all obvious how to do it. So again, the problem. So some NP problems turn out to have easy solutions, and some apparently don't. So then, how do we identify the NP problems that are hard? And the answer is, well, we have a notion that's the NP complete problems are the hard ones. And so how do we define an NP complete problem? Well, we have the notion of reducibility. So A is P reducible to B, and of course P stands for polynomial. Okay, A is P reducible to B. The problem is P reducible to B. If we had an oracle for B, that it could be used to efficiently solve A, meaning solve A in polynomial time. So in other words, if we had a procedure that solved B, a black box procedure, but we don't know how it works or anything, but somehow it comes up with correct answers. If we could use that to solve A efficiently, then we say A is reducible to B. And the point is, any good procedure for B, of course, then could be turned into a procedure for solving A. So the theorem is, if A is P reduced to P, and B is P, in other words, B is easy, then A is easy. So class P is robust in that sense. It's closed under P reducibility. Okay, so what about NP complete? The problem is A is NP complete. And first of all, it's in the class NP. And second of all, every problem A and NP is P reducible to P. So it's a very strong condition. Intuitively, if A is NP complete, it's as hard as any NP problem. And and then we'll call it the theorem, an easy fact. If A is NP complete and A is in P, then P equals NP. In other words, if you want to show P equals NP, it's sufficient to find any NP complete problem and give it a polynomial time algorithm. And then you prove P equals NP. And there turn out to be thousands of NP complete problems. And that fact is very tempting for the public who knows about this $1 million prize. And in fact, I get frequent email messages from people who think they found a Polytime solution for some NP complete problem, and therefore P equals NP. But they've all turned out to be wrong. Okay, so that's, I just said that. Okay, as I say, so what's remarkable is that thousands of problems have turned out to be NP complete. And most scheduling problems, like that of the sort I mentioned, jewelry, trucks, exam scheduling, etc., turn out to be NP complete. So here's an interesting example of a, well, we call it an exam scheduling problem. Let's say universities face this problem all the time. We want to schedule n examinations, but we have some limited number of time slots. And I'm going to say just 3 time slots, because already with just 3 time slots, the problem is difficult. So we have constraints because students take more than 1 exam, and obviously can't schedule both their several exams at the same time for a given student. So a conflict between 2 exams, you put an edge, you think of it as a graph, you put an edge with the nodes of the graph or the exams, and the conflicts are edges between a pair of exams. You put an edge between a pair of exams as some students is taking has to take both of them, and they can't be scheduled at the same time. And so you want the problem then is to assign time slots to every exam in such a way there are no time slots, if it exists. And part of the decision problem is maybe there's no solution, or determine if there's a solution. And this is in graph theory, this is known as graph tree colorability. The exams are the nodes of the graph, and the edges are the constraints, and then the idea is you assign one of 3 colors, red, blue, green, or whatever, to each node in such a way that adjacent nodes connected by an edge, do not have the same color. Is that possible? That's the question. So here's a simple example, and the Peterson graph, and the question is there a way of assigning colors to the nodes of the Peterson graph in such a way that, say, red, blue, green, in such a way that adjacent nodes have different colors, and indeed there is. So there it is. You can easily check, look at every edge, and notice that the colors at the endpoints of each edge are, in fact, distinct. So we say the Peterson graph is 3 colorable. Now, this graph, did I say it? No. This problem is NP complete, turns out to be NP complete. even with just 3 colors, the problem, given a graph in general, of course you think of hundreds of nodes, and is there a way of assigning colors, 3 colors to the graph, with satisfying this constraint? That's one of the hardest problems with NP. Okay, so let's talk a little bit about proving a problem is NP complete. So the definition and existence of NP3 problems goes back to 1971 and discovered by myself and then quite independently by Leonid Levin of the Soviet Union. And so his work didn't get shown to the West until 2 or 3 years later, unfortunately, because of the Cold War. But anyway, so the method I use, the standard NP-complete problem is the Boolean satisfiability problem here. And so a Boolean formula, a propositional formula, has variables x, y, z, and connectives and, or, and not. And then you build a formula out of those variables and connectives. And then the question is it satisfied? In other words, is there a truth assignment to the variables which makes the formula true? Or is there a 0-1 assignment? Because we computer scientists like to use numbers, so 0 is false and 1 is true. So can you assign 0 and 1 to the variables so that the formula is true? And so this turns out to be NP complete. And even the special case of 3-sat is NP complete. And in 3-sat, you're given a formula that looks like this. It's in conjunctive normal form. That means it's an and clauses in each clause like this has at most 3 literals in it. So X or not Y or Z is the clause. And you can have up to 3 of these things in the clause, but you could also have 2. And then the question again, is it satisfiable? And this special case turns out to be a 3-sat already turns out to be NP. And so here's another example of clause. Well, this one is unsatisfiable because it says that every pair of variables x, y, y, z, y, x, z has to be, at least one of them has to be true, and at least one of them has to be false, and so that's not possible. So, okay, so 3-sat is NP complete. That was in the original, my original paper in 1971. And incidentally, 2-sat, if you just allow 2 variables in a clause, then the problem, the satisfiability problem, has an easy solution. It's in polynomial time, in fact, a linear time. So we can take that as an exercise that we don't know how to do it. How do you easily determine whether a conjunctive normal form, a formula like that, with 2 literals per clause, has the satisfying assignment? So it turns out to be easy. Okay, so every NP, by definition of NP complete, every problem in NP is reducible to 3-sat. And so let's illustrate this by an example. In particular, 3 colorability, which is an NP problem, is reducible to 3-sat. So let's talk about how to do a reduction. In this case, it turns out to be relatively simple. We're trying to show, okay, that the 3 colorability problem is P reducible to the 3-sat problem. So we're given a graph, G with nodes B1 to Bn, say n nodes, and we're given a list of edges like B3, B5, B6, B6, and so on. And want to know if that graph is recolorable. So what we're going to do, since that's hard to do directly, we're going to reduce it to 3CNF. So we have to then turn this graph into a corresponding 3CNF formula. And with the property that that formula is going to be satisfiable only if the graph is recolorable. And so how do we do that? What's the formula going to look like? Well, it's going to have variables, Boolean variables like this. So R1 to Rn are in Boolean variables. Intuitively, Ri, if it's true, means that we're thinking of a truth assignment to these variables is going to describe a three-coloring of the graph. That's the idea. And so intuitively, we want to fix it so if Ri gets assigned 1 true, then it means that node I is colored red. And if Bi is true, it means node I is colored blue. And if Gi is true, it means Gi is colored green. And okay, so then we have to come up with clauses in the formula. These are constraints on the truth assignment. And we have to put clauses or constraints in that will ensure that any truth assignment satisfying all the clauses corresponds to a legal three-coloring of the graph. And so what are the clauses? Well, first of all, we want to make sure that any such truth assignment assigns at least one color to every node in the graph. And so here are the clauses. Node 1, we put R1 or B1 or G1. That means node 1 at least has to be colored by one of the colors, red, blue, or green. And we do that for every node. So we get n clauses, one for each node. Any assignment satisfying these things will assign at least one color to every node. Now, it could assign more than one color, but we don't care, it turns out, because if a truth assignment is a legal coloring that assigns more than one color to a node, you can get a legal coloring by just throwing in one of the extra colors for every node and you'll get a color. So that's not an issue, but what is an issue, of course, we have to make sure that the edges get different colors. Every edge. So here, what do? Well, fix an edge like B3, B5, and we put in these three clauses. This says R not R3 or not R5. So to satisfy this, you can't assign both node 3 and node 5 red. And of course you can't, because that would say it wouldn't be a legal color. And similarly, you do that for blue and for green. So that for every edge, you put in three clauses that look like that. And that's it. You take these n clauses, and then for every edge, you put in these three clauses. Take their and that is the 3CNF formula. And it's easy to see that that formula is going to be satisfiable if and only if the graph is three-colorable. Because if it's satisfiable, or these truth assignments satisfying, it tells you how to color the graph. And if you know how to color a graph, you can get a truth assignment satisfying the assignment. So this kind of reduction is usually pretty easy to carry out. And just emphasize why intuitively the satisfiability problem is NP-complete. It's easy to do this in general. There are easy reductions. And of course, you can carry it out in polynomial time. It's an easy carry out this reduction. Okay. Now, because in general, the satisfiability problem is NP-complete, and as I claim that in general, NP problems are easily reducible to satisfiability, then it makes stat solvers become very important. A SAT solver is a program that solves the satisfiability problem. And it turns out that there's a huge industry in making efficient SAT solving programs, even though, of course, the problem is NP-complete, so you don't expect it to work successfully on all inputs, but it turns out to work well on a large number of them, a surprisingly large number of them. So every year there's a SAT competition comparing some of these programs. And here's an example of incredible success that these programs can have, and even for practical problems. This is the problem of trying to verify parts of a Sun microprocessor, and you come up with a whole bunch of causes, and I guess if it's satisfiable, then you found a bug in the processor. And otherwise, well, you don't have a bug, at least as far as the way you assign the causes. But what's amazing is these numbers. So this Z-chat processor was able to find a bug in a CNF formula with 200,000 variables and 700,000 clauses. And you can imagine, I mean, obviously he wasn't using brute force because the number of possible truth assignments to 200,000 variables is exponential, 2 to the power of 200,000, which is unthinkably big. But it was able to find a satisfied assignment. And here, also impressive, showing with 85,000 variables, this example was unsatisfiable, proved that it was unsatisfiable. So these SAT solvers have amazing performance in some cases. So then you wonder, the SAT's supposed to be complete. How come these things can be so successful? And the answer is, well, they don't always work. And fortunately for RSA, an example is you can't break, as far as we know, cryptographic systems using this by reducing the problem to satisfiability. So in particular, if you try to reduce a factoring problem to the satisfiability problem, the SAT solvers choke. They can't factor. That's not a way of factoring, at least numbers. I don't think they can use factoring because the numbers in there, they just don't work. Now, as I say, complexity theorists tend to believe P not equal to NP, we also like to speculate what would happen in the world in which P equals NP. And let's think about that. Now, we're not only going to be fair here, we should assume not only does P equals NP, but in fact, so SAT would have, P equals NP means SAT has a Polytime algorithm. But, of course, that algorithm, Polytime, by the definition, wouldn't rule out an algorithm of something like n to the power of 100. But, so let's, empirically, natural problems, if they're in Polytime, don't have such strange, difficult algorithms that run power into the time into the 100. But let's assume the SAT not only has a Polytime algorithm, it has a truly efficient Polytime algorithm. And so that would make conventional cryptography impossible because in practice, the cryptographic protocols can be broken. They're NP problems. It's just an NP problem to break it. So you can rule out conventional cryptography, although you can still use quantum tricks and make cryptography work. And then, good news, all these, I don't know it's good news, broadly speaking, mathematicians can be put out of business. Now why? It's because if a mathematician can prove a theorem, then the theorem presumably it can be codified and written down in some reasonable number of symbols of 3 millions or 100 million, but some reasonable number. And the proof could be formalized. That's something logic can do. And we know how to use logic to formalize proof. So there would be a formal proof, and we assume it's not ridiculously long. The proof is not ridiculously long, then probably the mathematician couldn't find it. It's ridiculously long. So that would be an NP problem. Let's say that the question is there the proof of a given length? Because if the proof is there, you could verify it. So that's an NP problem. And if P equals NP, then you could find the proof. And so we could prove presumably all the 7 Millennium Prize problems. We could NP in this way. And you can make similar arguments for science and engineering, and a more speculative one that is composing beautiful music. And here you have to assume that there's some mathematical procedure that can recognize beautiful music. And if you make that assumption, or at least some subclass of beautiful music, if you make that assumption, then you could use the fact that P equals NP to find the expression that defines beautiful music, and then you could also use it to compose beautiful music, because you want to compose a beautiful piece. You want to, of course, you want to have some creativity, so you say it has to satisfy, your beautiful piece has to satisfy certain constraints, and other than that, it just has to be beautiful. And if it exists, then you can find this, you can find the music. Anyway, so all this is speculation. Now, okay, I should also mention here something about quantum computers. There is a standard mathematical model of a computer, so-called Turing machine, that goes back to Alan Turing in his famous 1936 paper, and on beautiful numbers with applications in China's problem. So this is the accepted general model of a computer. Even existing computers now, conventional computers, can be modeled reasonably by Turing machines. And but there are limits on, presumably there are physical limits on how fast ultimately they can be. I know we get faster and faster computers all the time, but surely there have to be limits. I mean, you can make an assumption, let's say, you can't pack bits in your memory by more than, say, the number of electrons in the computer, and the clock is limited by the speed of light between atoms. And if you make assumptions like that, then even if the whole Earth is a computer, the computer couldn't search through all 300-bit strings in the universe lifetime. So there have to be ultimate physical limits, except quantum mechanics. If you use quantum mechanics, physicists have come up with the notion of a quantum computer, particularly Richard Feynman and David Deutsch. David Deutsch gave a precise mathematical model, and then the model takes advantage of all these strange principles of quantum mechanics, like entangled states, and the fact that you can have qubits, superposition of states, so that with n qubits you could have 2 to the n possible bit strings it was taking on. And so taking advantage of these ideas, Peter Shor was able to prove that a quantum computer can factor in polynomial time. And so quantum computers, if they can be built, appear to be really, for some problems, like to be really fast. No one knows how to factor with conventional computers in polynomial time. However, the catch is, so far physicists haven't really been able to build quantum computers for more than a few bits. So that's an interesting question, whether can they really be built or not. And also, if quantum computers can be built, the experts say, well, they still probably can't solve NP-complete problems. And note that factoring problem is not thought to be NP-complete. It's a hard problem. It's in NP, but it's not thought to be NP-complete. And in fact, there's some feeling that there may exist polynomial time algorithm with factors, even a conventional one. That's an open question. So, the caveat. Still, quantum cryptography is a totally different issue because you can use quantum effects to send cryptographic protocols that can't be done in any conventional way. So you could still, even though RSA would be broken, you'd still have cryptography. And so, just nearing the end here, it's interesting to do some speculation. Will computers eventually be able to simulate the human brain? And this is, of course, the artificial intelligence problem. There's a whole subgroup of computer science, artificial intelligence, that more or less are trying to do that. And so these people think the answer is yes, the AI people. In fact, the brain is just a large, complex computer, apparently. So it should be just a question of time until we can build computers to simulate brains. Although this is not universally accepted, and you would try this as an example of a long-term critic who doesn't believe it. And here's a very respected physicist, Roger Penrose, that also is skeptical that he thinks, I've had a conversation with him, really thinks there's something going on in the brain using maybe physical things that we just don't use in conventional computers. So the notion of consciousness maybe can't be explained by, I don't know. Anyway, but speaking to consciousness, there is some computer science work by Manuel Blum, for example, trying to give a theory for the notion of consciousness. And so one final thought: if equals NP, would brains have evolved to solve NP-complete problems? Apparently, we can't solve them. So anyway, closing slide. Lance Fornall wrote a nice article on P and NP with ACM communications, and says the P versus NP problem has gone from an interesting problem related to logic to perhaps the most fundamental and important mathematical question of our time, whose importance only grows as computers become more powerful and widespread. So thank you.
For spending your precious time with us and enlightening us with your words of wisdom. And now all of you are requested to be seated at your places, as we'll now have an interactive session with Sir, and he'll answer your questions.
You have an NP problem, so can we factorize NP problem into P and NP and then go on factorizing the NP part of the factorized part, and go on doing so till we reach a point where we can drop the NP?
So I didn't quite get it. So,
Yeah, you have a NP problem.
okay.
So can you factorize that NP problem into a P part and an NP part, and then?
Well, so you want to break it into,
Yeah.
Well, the P, of course, the P part, maybe you mean just, it's the recognizing part. You have the verifying. So you have a, if it's an NP, then if you have a search problem, you can find an issue, you can verify it. So I'm not sure what you mean otherwise by the P part of it. Yeah, that has a problem in time.
What I was wondering was the more general and two-dimensional matching algorithm that you mentioned. Does that reduce to the famous algorithm of scale and shape for the case of a bipartite graph?
So this is the coloring algorithm we're talking about?
No, the matching.
Oh, the matching problem. Well, the matching problems are all, they're all polytime. So, in fact, it's easier for bipartite graph. The general one is much harder.